Okay, let's take suggestions for problems that you want to talk about. Okay, 44, 45. Okay, what else? Other suggestions? Yeah. 35? What else? So, 24, you were sketching horizontal distance on the Ferris wheel. Horizontal distance measured in feet and then measured in radius lengths. 29 was the toy race car, the coordinates of the final position of the toy race car. 31 was kind of a general coordinates for any circle with any radius. Find the coordinates of the point after sweeping an angle theta. .35 was this one, given some different coordinates, different quantities, and then there were some unknown quantities and coordinates, and you were answering questions about those. Any other suggestions besides 35, 44, and 45? Okay, I think I'm gonna talk about the toy car question because it's really important. It brings together a lot of principles that we've been talking about. This is what we spent most of class Friday dealing with, and so I think this is a really good question. Let's talk about this one, and then we'll talk about 35 and then 44 and 45. Okay, and then at the end of class we'll have the quiz. Okay. Okay, so 29. It's a little bigger. Okay, so 29. Here's the setup. The toy car is going around a circle of radius 4. It starts at the 3 o'clock position, and it travels an arc length of 19 meters to its final position down here near the bottom of the circle. And they want to know what those coordinates are in meters. If this is the point 40, then what's the coordinates of x and y? So in general, if we've got a point on a circle, just in the very most general sense, what are the coordinates x and y? How are we going to get those? If we've got a point on a circle, if we have a point on a circle, just most. All right, he said cosine and sine. X coordinate is generally, what is it? The cosine? Yep. And y coordinate generally is? Sine. Okay, so that's the first step, is to recognize that, okay, if we're it's going to have to do something with cosine and sine if we're going to get coordinates on the circle. So the next thing we want to ask is, what is the input? What's the input into cosine and the input into sine? So that may be a single value, or it may be an argument, it may be an expression, but as a whole, what's in the parentheses is what's going into cosine, what's going into sine. What kind of quantity is that? What does that have to be? What do you think? Okay. Someone said theta, someone said radius lengths. What about, so let's start with theta. Is it theta that goes into this?
However we want to define theta.
What's that?
Can it be radius, lengths, degrees,
Okay, and what are all those things? What are all those things? What are those things? What kind of quantity goes into cosine and sine? Angle measure. Angle measure. So we need angle measure to go in there. All right. So there's some angle associated with this final position at the toy car, and that angle starting at the 3 o'clock position is this amount of openness right here. Okay, so that's what we need as our input into cosine and sine. So how do we get that value of theta? If we want to use radians, how are we going to get that value of theta? What defines that value of theta? And I'm asking for a formula. I'm asking for what does that number mean? That number of theta. Okay, so yeah, all right. So how are we going to get that number of theta?
4 times 2 pi minus 19.
Okay, that just sounds like a formula to me. What is theta in radians? How do we get that number? Where does that number come from by definition?
Radius length.
Radius length of what? Yeah, so it's this arc length measured in radius lengths, right? It's the number of radii subtended by the rays of the angle, the number of radii. So 19 is the total length of the arc, and each radius is 4 meters. So how do we calculate how many radius lengths that is? If it's 19 meters total and each radius is 4 meters? Yeah, it should make sense, right? Should make sense. We're going to take the total length and chop it up into equal pieces of 4, and that ratio will tell us how many of them we have, how many radius lengths. And that number of radius lengths then is the same as the openness of the angle in radians. Radians, okay? And so that's what can go in here.
So that would be the same as saying S divided by R equals theta.
That's right. But so we're really getting at why. Why is S divided by R equal to theta? Because it calculates the number of radius lengths. Yeah, number of radius lengths, that's it. And radius length is the same as radians. Okay, so now, the output of these. So the output of cosine, what does that give? So we've got the input is angle measure in radians. What about the output of cosine and sine? What do they spit out? Okay, coordinates. Measured in what? Well, radians is angle measure, so it's not really radians. Yep, it's radius lengths. So the output, what cosine gives is number of radius lengths. And cosine specifically? Yeah, number of radius lengths right of horizontal diameter. Vertical diameter, thank you. Okay, number of radius lengths right of the vertical diameter. Okay, and similarly, cosine gives number of radius lengths above horizontal. Above horizontal. Okay, so let's find these values and see if we can make sense of the picture here. So let's actually find the values we've got so far. What do we got? .038, and sine is negative 0.999, and then round, is it 3? Do you round? Is that right? 2.9, right? So 9 and 3. Okay, so let's start with the y coordinate. Is this the number of meters that it is below the horizontal diameter? No, it's radius lengths. Does that make sense that it's radius lengths? The way where the car is. So why does it make sense?
If you were to imagine like the XY
Yeah?
For cosine, it's just barely to the right of the y-axis, and that corresponds to root 100.
Okay.
And then it's pretty far below, basically over 1 radius length the x-axis.
What about the very bottom of the circle? How many radius lengths below the horizontal diameter are we?
1.
1. So this is just a little bit above that. So it's almost 1 radius length below the horizontal diameter. So that should make sense. And then how far to the right are we? Just barely, right? It's red. So we're just barely a little bit to the right. So just a little bit to the right, and that's number of radius lengths, or 0.038 radius lengths to the right, and then almost 1 radius length below the horizontal diameter. So these numbers should make sense. But they wanted those coordinates in meters. So if this is the number of radius lengths, how do we get how many meters it is to the right? Yeah, so we're just going to do what? Multiply it by 4. Okay, sorry. So we're going to just multiply that by 4. So if each radius is 4, and we multiply by the number of radius lengths, we'll get the number of meters. All right, and similarly, if we're this number of radius lengths below, how will we get how many meters we are below? Multiply by 4. So this should give us the coordinates in terms of meters. Or the actual coordinates, right? Because if this point is 4, 0, then this has to be in meters. Okay, so let's get our approximation for that. So 4 cosine of 19/4, 0.150. So that's the number of meters to the right. And then 4 times this is at -3, if I remember right, 3.997.
Yeah.
So notice, it took a long time to do that because I want to make sense of every single thing in this problem. We make sense of getting that input angle from the arc length traveled. We make sense of just what cosine and sine mean, number of radius lengths to the right and number of radius lengths below. And then if that's number of radius lengths, we just multiply by the length of the radius to get how many meters to the right and below. So lots and lots of really important principles here in this problem. Anybody have a question? Okay, so let's go on to 35. This one. What is theta, the measure of the angle? Okay, so they want this angle, which is it's not from 3 o'clock. It starts here and then sweeps around to here. So not starting at 3 o'clock, but starting here, we want this angle theta. Okay, so how can we get that? What's the meaning of theta? What's the meaning of it? It's going to be the number of radius lengths subtended by the rays of the angle. So here's the first initial ray. Here's the final ray of the angle. So those rays subtend an arc length. We want to find out how many radius lengths that is. So the whole length of it's 26.17 kilometers. So how can we figure out how many radius lengths that is? Yeah. So we take that whole arc length, again, split it up, cut it up into pieces of how long? 1 radius length, 5 meters, and that'll give us the number of radius lengths. And that number of radius lengths will be the angle measure in radians. Angle measure in radians. Okay, what's this? 5 point what? 23? 5.2. So that's about 5.2 radians. Okay, so now these coordinates, there's two possibilities for these coordinates. They could be in radius lengths or they could be in kilometers. Which are they? And how do you know? So we got 4.8 and 1.3. Must those be in radius lengths or kilometers? Why? Yeah, so what's the maximum number of radius lengths we could be to the right? The maximum number of radius lengths we could be is 1. And what's this number? 4.8, which is almost 5, which must be then, these must be kilometers, right? So what would it mean? So this is then the number of kilometers above the horizontal diameter. So what would it mean to take 1.3028, which is how many meters we are above, and then divide by 5. So let's get that number. So let's get that 0.26. So taking that number of kilometers, dividing it by 5, what does that give you? What does 0.26 give you? Yeah, it doesn't. So this is giving us the fraction that this is of a radius length, or number of radius lengths, right? This gives the number of radius lengths above the horizontal diameter. So what's that the same as? If that's the number of radius lengths above the horizontal diameter, that should ring a bell. What gives us that? Sine. That's a sine of what angle? Theta? It's actually alpha. Okay? That would be the sine of alpha. Because sine of alpha would give us how many radius lengths that point is above the horizontal diameter. And that's exactly what this ratio does. It takes the number of kilometers above, divide by how long one radius is, so that's the number of radius lengths. So it's the same as sine alpha. Same thing with 4.8273. If I divide that by 5, was it 0.965? What does that number mean? Yeah, number of radius lengths to the right of the vertical. Okay? And that would be the same as? Of? Alpha. Yep, cosine of alpha. What's next? So we got theta. We know what those two are. What's the value of alpha? So this is kind of going backwards. We know that, let's just work with sine. Sine of alpha equals 1.3028 over 5. That's what we just talked about. So going backwards, so we need the, remember we talked about the inverse relationship. So the inverse relationship would have this as its input, and that would be the output. Right? Because in an inverse, the input and output switch, right? We talked about that a couple months ago. So the inverse relationship of sine would have the vertical distance in radius lengths as the input and would spit out the output. So that's called the inverse sine. And you can just do second sine in your calculator, and that should give you some angle that should make sense. This is going to be more or less than 1 radian, do you think? Less. More or less than half a radian. Yeah, we know 1 radian is about like this. So we're thinking maybe this would be 0.4, 0.3 radians. Okay? So what do you get when you do that? Point what? 0.264 radians. Makes sense. A little bit more than a quarter radian. Questions on this problem? We good? So what was the next one? Going the wrong way here. A little smaller. Oh, wow, I should be working here. That's fine. Okay, so there we go, that's better. So Hope travels 0.33 radians per second. How many radians does she sweep out in t seconds? To find a function that gives the horizontal distance to the right of the vertical diameter. Okay. So all we have to do is make sense of this 0.33 radians per second, and we can answer this first question. And so what I suggested was make a table. So 0.33 radians per second. So just think about what that means. 0.33 radians per second. So in 1 second, how many radians? Yeah, so it's saying every second you go 0.33 radians. So in 2 seconds, it's 6.6. In 10 seconds, you're going to go 10 of those, right? Every second you go that many radians, so in 10 seconds, you'll go 10 of those, or 3.3. Okay? How about in t seconds then? So in t seconds, you'll go 0.33 t radians. So that's how you can write theta, how many angles theta you sweep out every t seconds. If it's 0.33 radians every second, then you're going to do that number for every second. So in t seconds, you'll do that t times. You'll do 0.33 radians t times in t seconds. That's 0.33 t. That equals theta. So to find a function j, horizontal distance is as a function of time. So if we want horizontal distance on the Ferris wheel, just in the most broad general sense, what are we going to need to get horizontal distance on the circle? They're saying cosine. Agree with that? Yeah, you're going to need a cosine. Something to do with cosine. That's going to give horizontal distance, or x-coordinate, on the Ferris wheel. Okay, so what goes into cosine? So we may have, it may be something complicated, but as a whole, what is that thing that goes into cosine? Angle, right? Angle. So, but we want that angle in terms of t because it's a function of t. So what's the angle as a function of t? Yeah, that's what we just found here, right? So this is telling us what the angle is for any number of seconds t. So since it's angle, we can put it right here. Because that is the angle. That is how much angle you sweep in t seconds. So it's a valid input into cosine. All right, so we want horizontal distance to the right of vertical diameter. Okay, so now if we just left it like this, what would the output be? What would it be giving us? So it gives us horizontal distance, but in what? radius lengths. Okay, so what's the maximum that will be? When will it be 1? At what time will it be 1? Someone said time equals 0. At what time is the horizontal distance to the right of the vertical diameter maximum? Time equals? 0. That's 0. That's right. At the starting point. You're at the 3 o'clock position. And you're at the maximum horizontal distance. So when time equals 0, the value of this will be 1. Okay? Over what time interval does the ball complete 1 revolution? Okay? So when does cosine complete 1 revolution? So for what angle does cosine complete 1 revolution? 2 pi. So if we take this right here, and we want to know the specific time period that achieves an angle of 2 pi. Right? So we want to know when is that expression, what value of time makes that expression 2 pi, because we know cosine makes a full revolution at 2 pi. So we solve for TP, which is, I'm calling the period. 2 pi over, which is 6 pi. So it takes 6 pi seconds for 1 revolution. Sketch the graph. Okay? So we're going to sketch this graph based on all this information we have so far. And then we can check it. Let's see here. Okay, so maximum. So we said at time equals 0. Oh, let's see, 6 pi seconds. What is 6 pi seconds? You're going to need to zoom out here. So what is 6 pi seconds? 18.85. Okay, we'll just have to draw over the top of that work over there. That's fine. Okay, so at time equals 0, what did you say the horizontal distance to the right was? Right, 1 radius length. Let me draw just a quick picture here. Okay, so at time equals 0, we're here. And this is going to give us horizontal distance to the right in radius lengths. So at time equals 0, what's our horizontal distance in radius lengths? 1. So we're going to start right there. Now, this is my time axis here. So what is the period, or what's the length of time that's going to take for 1 full cycle of output values? We calculate it at 6 pi. So what is 6 pi? 18.85? Right here. So when we draw these cosine and sine curves, it's convenient to break it up into 4 equal pieces, right? First quadrant, second quadrant, third quadrant, fourth quadrant. So you take that period and we're going to divide by 4. So you say, let's see. So 18 pi, 6 pi, divided by 4. That's how long each fourth is. So the first fourth is 4.7. Okay, and then halfway is going to be 2 of those, 9.4. Okay, and then we'll add another 4.7. $14.1. So basically, however you want to break that thing up into fourths, get those 4 breakpoints 4/4 of your period. In this case, the period is 18.8 or so. So get those fourths and break it up, and then just do it 1/4 at a time. So you said that it starts at 1 radius length to the right. In the first quarter circle, it will go from 1 radius length to the right to what? So at the top of the circle, how many radius lengths to the right are we? 0. Okay, so this will be a point right here. And we know it's not a straight line. We know that at first, those decreases are what? Small or large? Small, and then the decreases are? Larger. Okay, larger. So these decreases are getting more negative. So is the rate of change increasing or decreasing? If those changes or the rate of change is getting more negative. Decreasing rate of change. This is decreasing rate of change, getting more negative. Okay, next part of the circle, we're 0 to the right. Next quarter, we end up -1 or 1 to the left. So we're going to be down here. At first, the changes are negative and relatively large negative or small negative?
Large.
Relatively large and get smaller negative. Increasing or decreasing rate of change?
Increasing.
Increasing. Those changes get less negative. We get the most negative changes at first, and then the changes become less negative. Increasing rate of change. It's on the test. Changes becoming more negative, changes becoming less negative. So decreasing rate of change, increasing rate of change. Okay, next quarter. We're at 1 to the left, or -1, and we end up at 0 radius lengths to the right. So after 3 quarters, we're back at 0. Changes at first. So these positive changes or negative changes? Nope, these are positive changes because they're getting greater, right? They're getting greater. You're getting more positive. So are they getting more positive or less positive?
More positive.
More positive. The smallest positive changes are here. The largest positive changes are here. So the rate of change, increasing or decreasing? Still increasing because the changes or the rate of change is becoming more positive. So that's increasing rate of change. Finally, we're at 0 to the right. In the last quarter circle, we end up at, from 0 to the right of the vertical diameter to 1 radius length to the right. So when we make it full circle, we're back here at 1. The changes becoming more or less positive. Is this a large positive change relatively or small? No, we're measuring horizontal distance. So this first change is large, right? And then the changes get smaller as the direction becomes more vertical. So the changes or the rate of change is becoming less positive or decreasing rate of change or decreasing changes. Okay, so that's our sketch of this in terms of radius lengths. So let's put in our function, and it should be the same thing. So our function is cosine of 0.33t x. So I got to put x. Do that. Yep, got it right. Okay, so I'm graphing it in red. We'll see how we did. Okay, so that's the actual graph of cosine 0.33t. And so it checks out. Is there more to answer on this question? Was that the last thing? Any questions on this one? Yes, sir.
I know this might be kind of menial, but if you calculate 2 pi over and divide it by 0.33, it's 19.04 and not 18.85.
Oh, yeah, I assumed this was 0.3 repeating.
Like how?
Yeah, so.
Does it really matter? Like on a test?
Yeah, I just made an assumption that this was 1/3 when it's not. It's actually 0.33. So we're just off by a little bit. So it's only off by starting with the hundredths of a whatever that is, or thousandths even, tenths, hundredths, thousandths. So
it's just a matter of the number, but it's the same idea.
Yeah, it's just we just have a slight precision error because I assumed that was 1/3, and that's not quite 1/3.
Gotcha.
Yeah. Other questions? That's a good point, though. I just overlooked that. Okay. We can do this last one quick. So 45 says it's the same idea, but now it tells you 75 seconds. So now it says it takes 75 seconds to get around. And we want vertical distance above horizontal diameter. But everything else is the same. Okay, so if we want vertical distance above the horizontal diameter, what will that be? That'll be sine. So it'll look something like this. The angle will be something like this, BT. So the question is, what is this coefficient, B, that will get us a period of 75 seconds? All right, so the quantity BT, what kind of quantity is it? It's an angle, right? So if we want a full rotation, what value of the angle gets us a full rotation? 2 pi. So when the angle is 2 pi, we want the corresponding time to be what? 75 seconds. So this will help us solve for B. So B times the time period needs to equal a full period in angle. Does that reasoning make sense right there? We need the value B such that when the time is 75, it'll make that expression equal to 2 pi. We'll get one rotation. So what is B? 2 pi over 75. Okay, so our function is 2 pi over 75 t. Is it like j of t or something? Is that what they asked for? Call it j? No, m. M of t. Okay, so let's sketch this. So if this is our time axis down here, what time gets us a full rotation? Yeah, they told us, right? 75 seconds. That's the time rotation. So I'm going to come out here to 75. And then what are we going to do to sketch this? What are we going to do with the 75? Yep. Break it up into 4. So 75 divided by 4 is 18.75, or about 18 or 19. Is that right? Yep. Okay. So then divided by 2, 37.5, and then add that 18 number again, somewhere around 55. So there's 75 chopped up into 4 equal segments. So now we want vertical distance above the horizontal diameter. Okay, so at the start, at time equals 0, what's our vertical distance above the horizontal diameter? 0. After a quarter circle, what's our vertical distance above the horizontal diameter? 1 in radius lengths, right? Next quarter circle, now what's our vertical distance? Back to 0 again. Next quarter circle, 3/4 of the way around. Vertical distance above the horizontal diameter, -1. All the way around, vertical distance above horizontal diameter, 0. Okay, we could talk about changes in rate of change. Rate of change decreasing, rate of change still decreasing, rate of change increasing, rate of change increasing. So if we put in, do that. So I want sine of 2 pi divided by 75x. I'll make it purple. No, I'll make it blue. So get that. Got it. Okay, any questions on that? That was a crash course problem. So we got to take our quiz. So just any extras, just leave them over there. You don't have to give them to me. I'll come get them. Start at the top. Oh, I don't